We're talking quantum mechanics, computers that work like our brains, and a whole new type of electronics. Get this. Scientists have discovered a new quantum force called the anomalous Hall torque, and it could completely change the future of computing. So let's break it down, starting with spintronics. Spintronics aims to harness the spin of electrons to revolutionize electronics. You might be thinking, hold on, what's electron spin? Picture this. Every electron is like a tiny spinning top. And that spin, well, it creates its own little magnetic field. It's this spin that we can use to store information and process it in ways we never could before. Now, here's where it gets really interesting. This new force, this anomalous Hall torque, it lets us manipulate electron spin incredibly precisely. It's like we have these tiny, tiny fingers that can flip these electron magnets however we want. It's wild. And it could lead to some truly mind-blowing spintronic devices. Think about it. We could be on the verge of a quantum leap in computing. But how does it actually work? And what does it mean for the future of, well, everything? Let's start with the basics. Spintronics uses the spin of electrons instead of their charge, which is what powers traditional electronics. Instead of just electrical currents flowing through wires, we're talking about actually controlling the direction of these electron magnets. It's a whole new dimension of possibilities. Instead of just ones and zeros, which is how our current computers store information, we can use the up or down spin of an electron to represent data. It's mind-boggling, right? Now we've got these spins, and this anomalous Hall torque can manipulate them. But why is this particular torque such a big deal? Well, it turns out it completes a triad of Hall-like spin-orbit torques. This is a huge deal for anyone working in spintronics. Think of it like this. Scientists now have a complete toolkit for controlling electron spin. Each torque offers a different way to manipulate these tiny magnets, giving them incredibly fine control over how information is stored and processed. And that control is key for building the next generation of spintronic devices, things like spin-torque oscillators. These things could be the basis for a computer that mimics the human brain. Imagine computers that learn and adapt like living things. Instead of processing info in a linear way like our current computers, they'd work more like the intricate networks of neurons in our brains. Pretty amazing, right? So how do these spin-torque oscillators actually function as artificial neurons? Well, each oscillator can be tuned to have a specific resonant frequency. It's kind of like how a neuron has a specific firing rate. And by connecting these oscillators together in these really complex networks, scientists think they can create systems that behave a lot like the human brain. Think about that. We could be talking about building the fundamental building blocks for a whole new type of computing. This could revolutionize AI, machine learning, even how we understand consciousness itself. But wait, hold on. How do we actually build these spin-torque oscillators? What materials are we talking about here? This is where the anomalous Hall torque comes in. This new force gives us much finer control over the magnetization dynamics within these oscillators. It makes them more efficient and hopefully easier to manufacture. It's like we've discovered a brand new tool that lets us sculpt these tiny devices. We can tailor their behavior with incredible precision. And that's what makes this discovery so exciting. It's not just about making faster computers. It's about opening up whole new ways of exploring the very nature of computation itself. Okay, so we've got these spin-torque oscillators that can mimic neurons, and we can control them really precisely using this anomalous Hall torque. But what are the real-world applications of all of this? What can we actually do with it? Honestly, the possibilities are pretty much endless. Imagine computers that are so intelligent they can solve problems in a fraction of the time it takes our current machines.
Or robots that can navigate and interact with the world in a truly intuitive way. We could even see breakthroughs in medicine, like personalized treatments based on a person's unique genetic makeup. But it's not just about practical applications, it's about pushing the limits of what's possible. Harnessing these quantum forces, we could create devices that learn and adapt like living organisms. You might even blur the line between artificial and biological intelligence. And that's what's so fascinating about this field. It's not just about cool gadgets, it's about expanding our understanding of the universe and our place in it. Now, before we get too carried away with these futuristic ideas, let's step back for a second. There are still challenges ahead. Building large-scale networks of these spin-torque oscillators, making sure they're stable and reliable, figuring out how to program these systems to actually do complex tasks, these are all big hurdles that researchers are still working on. But the progress they're making is incredible. It's clear that this field is ready for some major breakthroughs in the coming years. But how do we actually build these things? Well, it all starts with the right materials. You see, we need materials that can conduct both charge and spin efficiently. It's kind of like we need a material that's like a superhighway for electrons, allowing them to zip along with their spins all lined up. Some materials, like certain types of magnets,
already do this naturally, but finding that perfect material with all the right characteristics, that's a constant challenge in spintronics. And it's not just about finding a material that can conduct spin, it also has to be compatible with the way we make things now. We're talking about creating stuff at the nanoscale, manipulating matter atom by atom. It's like this super delicate dance between precision engineering and material science. Imagine you're trying to build a house of cards, but with tweezers, and the cards are only a few atoms wide. That's the level of precision we're dealing with in spintronics manufacturing. Researchers are always pushing the limits of nanofabrication, trying to develop new ways to sculpt these tiny devices. But even with the best techniques, there are still challenges, like making sure these devices are stable and reliable is super important. You wouldn't want your super intelligent computer to crash because a few atoms are out of place, right? Researchers are working on ways to make these spintronic devices more robust so they can actually handle real-world conditions. And then there's the question of scale. Building one spin torque oscillator is one thing. But imagine trying to create complex networks of these devices, all connected in specific ways. It's like going from building a single Lego brick to building a giant functional Lego city. So there you have it, a glimpse into the incredible challenges and amazing opportunities that lie ahead in the world of spintronics. It's a field with so much potential, driven by this desire to understand and harness the quantum world. And who knows, maybe someday, thanks to all the hard work of scientists and engineers, these spintronic wonders will change our lives in ways we can't even imagine right now. That's the amazing thing about science. It's always pushing the boundaries of what's possible. And on that note, that's a wrap on our deep dive into spintronics. Until next time, keep exploring.